Okay, so let's look at the Applied Cryptography and Trust module. The module itself will be delivered through 10 main units. There are 2 assessments. The first is a test which will cover the first 5 units, and the second will be a research paper focused on the second part of the module. The topics covered include cryptography fundamentals, symmetric key, hashing and MAC, asymmetric encryption, key exchange, trust and digital certificates, tunneling, cryptocurrencies and blockchain, future cryptography, and host security. And the importance of the topic is highlighted through GDPR, which calls for increased encryption of data in order to protect the privacy on the data, but also to make sure that we can prove identities and thus allow access control. There's also an increasing requirement for pseudo-anonymity and also even anonymity, so that we can make sure that citizens' data is not identified to them. Along with this, we see an increasing requirement for citizen rights to be able to access their own data, and a requirement to be able to detect, respond and investigate around incidents. So one thing that we should say is that encryption works great until it doesn't. The methods we'll investigate are good in themselves, but obviously it doesn't stop others from making a mistake or for us not to have integrated security. So encryption works great until it doesn't. Encryption works great as long as no one makes a mistake, unless something goes wrong and unless everything works right. And what we really want to do is to make sure that Bob and Alice can communicate with each other in a trustworthy way, and where we can protect the privacy of the data transmitted, and also that they are able to identify each other to themselves. But we also have Eve, and Eve might want to listen to the communications, might want to spoof them, might want to intercept their communications. So we need to understand what the opportunities would be for Eve to do these things. And as we'll find, we also need an important actor known as Trent. And Trent is the trustworthy entity that both Bob and Alice trust. So through the module delivery, we'll be using YouTube for the lab demonstrations and for lectures. Teams will be used for the general communications around the module. And we will use Overleaf later on in the module and able to investigate how we can write a research paper. There's no requirement to use Overleaf, but it's a good platform to be able to write research content, and might be useful for writing dissertations. There'll also be some output on social media, and we'll give you some ideas of some of the entities that you might want to follow. SecuritySite.com contains lots of examples of code and methods that you can analyze. But overall, the main content for the module is contained within this GitHub here. It will be kept up to date, and each week there'll be up-to-date labs and lectures, hints and tips and so on. So as I said, the module delivery is through YouTube for the content for lab and and for lectures and lab demos. Overleaf is a possibility for coursework submission, and then in the labs we're using a Ubuntu instance, either in VSOC, or you can download your own Ubuntu or even build your own Ubuntu instance. As part of that, we'll be integrating with Python to be able to demonstrate some of the key methods. Along with this, we'll be using OpenSSL to be able to show how we can use command line integration. And along the way, we might stop by and have a look at Node.js, which is an equivalent to Python. But each of the labs and the code related are stored inside this GitHub. In terms of the timetable, we'll go through each of the main units, and then we will take these units and they will feed into the first test. Along with this, we'll start to work on the coursework after the first test, and the coursework submission happens in week 15. Okay, so week 9, 50% test here, and then in week 15 we have a coursework again worth 50%. One thing we'll find is there's no one magical method that will solve all our problems. We have key exchange methods, as we'll find Diffie-Hellman, elliptic curve Diffie-Hellman. We have encoding methods such as base64 hexadecimal to represent our bit streams. And often we use symmetric key encryption to be able to encrypt our data, such as AES and ChaCha20, and then we use a hashing method to be able to provide a digital fingerprint for our data to know that it's not been changed. And then to provide identity and digital signatures, digital signing, we often use public key encryption. And we need a way to be able to transport our public keys, as we'll find out, and for that we use digital certificates or the PKI, public key infrastructure. Along with this, we see other methods that we need and that are focused on privacy, such as zero knowledge proofs, homomorphic encryption, digital signing, and so on. And those have all got to integrate with policies, rights, governance, auditing, and so on. So really this is a schema that would allow us to be able to make sure that Bob and Alice communicate in a trustworthy way. And we'll find that each of the elements around cryptography fits together to create a bigger picture. So the first unit we'll be looking for is just some of the basics around encoding, what key encryption looks like, and some traditional ciphers from the past. Then we'll look at frequency analysis and some other key concepts such as random numbers, prime numbers, and big integers. And then very simple operations that we perform inside cryptography, such as the mod operation, XOR, and bit shift. Then we'll look at symmetric key, the workhorse of the industry, and how we can add salt methods, how we can salt our encryption to make sure that it's forever changing. So for that, we'll look at block or stream ciphers as part of that. And then an important area is key entropy, understanding how secure our keys actually are. Then we'll move on to hashing methods, and we'll look at the typical methods that we will use, such as MD5 and SHA-1 and so on, especially looking also at the slow hashing methods such as bcrypt and PBKDFS2. Then how we take a password and then create a hash of it is very important in terms of creating encryption keys. And along with this, we'll look at what are called timed one-time passwords, where we can create a password that only exists for a certain amount of time. And then finally, we'll look at what are called MACs, or message authentication codes. In Unit 4, we'll look at the principles of asymmetric encryption or public key encryption, where Bob and Alice have a key pair, a public key and a private key, and where we can distribute our public key to anyone who wants it, but we use our private key to be able to sign for things and prove our identity. As part of that, we'll look at the core methods around RSA and elliptic curve, and then how we can use the private key to authenticate ourselves. And finally, we'll be looking at an example of signed email, where we can prove both the integrity and the signer of a message. Then we'll move on to key exchange, a very important area where Bob and Alice can communicate and they end up with the same shared key in the end of it, and Eve can't tell what that shared key is. As part of that, we'll be looking at the Diffie-Hellman method, which many systems are built on, and then how we can use more modern methods such as the elliptic curve Diffie-Hellman method, which is used in most key exchange methods now. From there, we'll be looking at PKI and trust infrastructures, especially looking at digital certificates and how we can use them to be able to create our public key infrastructure and create signatures. After this, we'll look at tunneling, and in tunneling, we'll be looking at the main standard for that, which is SSL, TLS, and how we can exchange our keys. We can build on this, then looking at SSH and how we can use remote access methods and tunnel through with a TLS infrastructure. And then we'll touch on a VPN type infrastructure with IPsec. Then looking more towards the future, we'll be looking at blockchain and cryptocurrencies, especially looking at Bitcoin and Ethereum, and also into the integration of smart contracts. Then, as part of the coursework, we'll be looking very much into the future and seeing how our cryptography methods are developing and where they may end up. So for this, we'll look at zero-knowledge proofs, how we can prove something without giving away the core data. Homomorphic encryption allows us to be able to process data without actually revealing the data contents. And lightweight cryptography allows us to be able to run cryptography or encryption on fairly limited devices. And then when quantum computers come along and where they can crack our existing public key methods, we'll have a look at some of the quantum robust cryptography methods that might be used to replace these existing methods. So those are the units that we'll be covering over the next, over the course of the semester, and we hope you will be supported in your learning of these. Thank you.